Well, thank you very much, everybody, and welcome to the 9th of our Gresham lectures on net zero. Although this lecture will be a bit of a departure from all of the lectures to date, which have been focused on the challenge of how do we stop global warming, how do we stop the rise, therefore, in essentially one number, the global average surface temperature. But of course, that one number is, as I emphasized in the last lecture, hard enough even to measure, never mind feel or experience. And what really matters to people in terms of impacts of climate change is what's happening to our weather. So in this lecture, we'll be talking about the two ways in which climate affects weather. So there's, you can mull over and you say, why are the two ways? And we'll talk about this. So building on that, we'll talk about how we set about quantifying the role of climate change in extreme weather events in particular, because it tends to be the extreme weather events that do the damage, and why it is that getting this right is really starting to matter.
The Gresham College lecture that you're listening to right now is giving you knowledge and insight from one of the world's leading academic experts. Making it takes a lot of time, but because we want to encourage a love of learning, we think it's well worth it. We never make you pay for lectures, although donations are needed. All we ask in return is this: send a link to this lecture to someone you think would benefit, and if you haven't already, click the follow or subscribe button from wherever you're listening right now. Now, let's get back to the lecture.
I mean, at the end of the day, weather, like this storm in Lahinch in the west of Ireland, it matters much more than global temperature. I mean, this is what actually affects people's lives and livelihoods. But we have always had extreme weather, and this is a photograph I took just down the coast from Lahinch, showing that same winter of storms that destroyed this pretty old wall here. So, it was a 1 in 100 year, perhaps, event, as we assessed at the time. But as you can tell, there's some infrastructure there that had no problem with the storms, been around for a bit longer than that. And that gives you a sense of the perspective we have to take, that, you get a 1 in 100 year storm, but it's not a 1 in 1,000 year storm. And that's the kind of thing we'll be talking about in this lecture. And the reason it matters is less. One thing I do get teased about is our obsession with flooding in the Thames Valley. You're going to hear a lot about flooding in the Thames Valley in this lecture. And for those of you who live in the Thames Valley, I'm sure you'll find this very interesting. But I am occasionally teased by colleagues who point out that the floods that actually matter are probably not the ones that happen in OX1. But that's been a focus of our attention. But so this is some very, very serious floods that happened in Bangladesh a couple of years ago, and it's this kind of event that was being much discussed at the recent COP28 meeting in Dubai, where countries have agreed to contribute to a fund to pay for loss and damage due to climate change, which of course raises the question of how do we tell what is loss and damage that's due to climate change? And that's already becoming a contentious issue. How are you going to decide what events should get payouts from this fund? But we're going to talk about, as I said, more parochial level, OX1. And this is really what prompted my interest in this whole topic back in 2003, so just over 21 years ago. I was looking out the back door of our house at the floodwater of the Thames getting steadily closer. And this was the scene at the neighbour's house, and then just actually Dave Frame, who I mentioned in the trillionth ton lecture, who I've worked with extensively. That's his front door, just there. Fortunately, he was renting the house, but flooding is very traumatic for people. We were pretty concerned at the time because you couldn't get sandbags for love nor money, and the water was getting closer. We were very lucky; we didn't actually end up getting flooded, but plenty of neighbours did. And at the time, the sort of mantra of the climate science community was, weather's not climate. These are weather events. When you're talking about climate, you're talking about global averages, global average temperature, and so on. These weather events have nothing to do with that. And the thing we kept on saying is you cannot attribute any individual weather event to climate change. And this frustrated me because you had a feeling that, there was something to be done here, which prompted this article. And the reason, of course, it was sort of starting to this line, you can't associate a particular weather event with climate change, was starting to wear a bit thin because people were saying this is a 1 in, we had a whole lot of floods in autumn 2000, we'll come back to those. And at the time, everybody said, this is a 1 in 100-year event or so, and there was a lot of discussion about. And then 3 years later, we had the same thing. And so it's like, well, okay. And that's the point where you start to think, okay, so what can we say about the role of climate change in these events? And this is kind of what it boiled down to, and this is a line in this article I was particularly proud of, quoting Ed Lorenz, who I think in turn was quoting Mark Twain. Climate is what you expect, weather is what you get. So we'll talk a bit about what we mean by expect and get in a minute. And then the flip side of that is, well, climate is what you affect. When we put greenhouse gases in the atmosphere, we affect the climate, but it's weather is what gets you. Because it's the weather that actually affects us. So if we talk about sort of what we mean by what we mean by expectation, we'll come on to that in a minute. But the question of attribution, of linking weather events to external drivers in some way, has been around for some time. And I came across this preparing for this lecture. This was in the 1915 Quarterly Journal of the Royal Meteorological Society, and they were talking about another wet winter that occurred in 1415. And this is a quote from the paper, an explanation which has been most readily accepted by the general public, Gresham audiences of the time, for example, and even found favour among a few meteorologists, is that the heavy artillery firing in France and Flanders is the primary cause of the unusual wetness of the winter. So people have looked for explanations for weather events since time immemorial. And of course, if you go further back, you can find that poor old Edward II basically lost the support of the population because of a famine, which was blamed on him for being an evil king, but it was just a famine. Anyway, so let's talk a little bit about what we mean by climate is what you expect and weather is what you get, with the help of a dice, a very familiar dice, and I'm going to ask an audience member, if you don't mind, helping out here, because it's always more convincing if I'm not the one who's throwing it. So if you could roll the dice for us, somewhere around here, I think they wanted it, and call out what you get.
It's a 4.
A 4. Let's try again. Just keep rolling it a few times. You've got to roll it a few times. 3, 2. This demo doesn't always work. Okay, let me try. There's actually, okay, we got a 6. We got a 6. We got a 6. We got a 6.
Loaded dice.
But it didn't work to start with. That's the thing about a loaded dice. And it's just the same with the climate. Yes, heat waves are getting more likely, but it doesn't mean you're going to get a heat wave every year. Cold winters are getting less likely, doesn't mean we're not going to occasionally get a cold winter. So actually the demo kind of works, because it's obvious now. It took about 2 6s before you started to think, wait a minute. And by the way, I didn't switch the dice. It was the same dice, in case you're wondering, because we sort of suddenly. But thank you very much. You're fired. It is actually I'm sure there's a whole PhD to be done on what actually happens when you roll the dice, because it is interesting how once I got the knack of it, I was getting a 6 every time. But you can easily not get a 6 every time. So anyway, But the point is, so we expect to get a 6 1 in 6 times. That's what we mean by the climate of the dice, of a true dice. Yeah, and what we get is whatever the number turns up. So that's the analogy to have in your mind when you're thinking about climate and weather. And climate change works like loading the dice, slowly increasing the loading on the dice. So if I had switched the die, I didn't, honest, in that would have been like a climate change. I would have changed the climate of the dice by adding some loading to make it more likely it came up to 6. So that's an analogy to bear in mind, and it helps us, just thinking about a dice, helps us think about the whole challenge of understanding the link between weather and climate. So here's a plot, which, again, you could probably do in your head, telling you what the probability is in the horizontal of rolling a certain number of 6s. And obviously on the first roll, the probability is 1/6, if it's a true dice. The red dots are a true dice. And then if you want to get 2 6s in a row, it's... Anybody want to shout out? 1 in 36. There you go. And then the mental arithmetic gets a little bit trickier now. With 3 rolls, it's 1 in, 6 cubed, and so on. Okay? So that's what it looks like. The probabilities go down very rapidly as the number of 6s go up. So as soon as I rolled 3 6s, you were all going, oh yeah, it's obviously fixed. I mean, because there would have been I can tell you, it would have been, to get 3 6s in a row would have been more than 1 in 100. This is the same data, but I'm just plotting it because you'll see lots of graphs like this through this talk. I'm plotting it as with probability 1 in 10, 1 in 100, 1 in 1,000, 1 in 10,000. And I'll probably start talking about return times, and when in weather and floods and so on, when we talk about the return time of something, we're not really talking about a time at all. It's not the amount of time you have to wait to get the next one. It's the probability of that thing happening this year. Well, 1 over the probability of that thing happening. That's what we mean by the return time of an event. So the return time of a 666 with just 3 rolls is 1 in 120. If you did it every day, it'd be 1 in 1 6 cubed, whatever the number is. 200 and something days. You'd expect to get that once that sort of frequency, and so on. Now, of course, if we just load the dice to make getting a 6 a 1 in 5 rather than a 1 in 6 chance. So I sort of load the dice a little bit. This particular dice is very heavily loaded, but imagine you have a sort of fairly subtle loading on the dice. That changes the chance of getting a single 6 from 1 in 6 to 1 in 5. But the chances of getting a double 6 go from 1 in 36 to 1 in 25. Okay? And the chances of getting a treble 6 go up even further, and so on. So what the loading does, it has some impact on the normal events, if you like, but a really extreme impact on the more extreme events, or a different impact on the extreme events than the normal events. And we have to understand that. Now, this is just a loaded dice. Now, it's not generic to everything, but it tells you that you've got to understand how this slope, the way things get less probable as they get bigger, which is a feature of many, many things, changes as a result of the loading, is something we need to do a lot of research on. And this is, we've jumped now from climate research you can do with, fluid in pipes and a handful of equations to the most sophisticated questions that confront climate researchers today, which is understanding what is happening to extreme weather, and for which we have to use the most sophisticated models we have available, which we will come on to. And I'm actually very happy to say that a couple of people who are actually doing this work are actually here in the audience. So just to remind you what return times look like, and this is a boring process, if you like, just a completely random process. If I was to roll a dice, a true dice, lots of times and add up the dots, I end up with something called a Gaussian distribution, a normally distributed process, the sort of bell curve of probability you expect. And if I plot here number of standard deviations in the vertical of my bell curve, what's the probability of getting one if I just generate lots of them? And the red dots here are lots of possible, lots of weathers. Weather is what you get, lots of rolls of this process. And you can see they go up. It's not a straight line, unlike the dice. It curves a little bit. And it flattens out as you get towards higher and higher, lower and lower probabilities, higher and higher return times. The blue is the sort of what you get if you have if you try it millions of times, so that you get a sort of very exact estimate of what the return times are. And the red shows you that when you're getting to a few tries, it starts to jump around a bit because you're in the noise at that point. Right. But let's think about a more interesting. This is a kind of boring process, one which is very familiar. This Gaussian process, and you could use, if you knew what you're studying was a Gaussian, you could work out from its behavior down here, you could make a very accurate prediction of what the chances would be of getting a particularly high magnitude event. You could use what you know about the process here to predict the probability of what happens out there. But that's the hallmark of a Gaussian process, is that you're rolling the dice, and each roll is independent of the previous one. But let's think about another process that also has a lot of randomness in it, but watch carefully. This is sand pouring out of a tube, onto a disk, and you can see how it evolves. It climbs up and then it slides down. Now, and then you get a big landslide, so to speak. And what's different about this process is that one grain of sand rolling down bumps into another one. And actually, it's not like rolling a dice. It self-reinforces. So it's what we call self-organized criticality. But I mean, it's a hallmark of chaotic systems, non-linear systems, which feed on themselves and don't, although actually interestingly, this is where the demo goes wrong. And if you watch this video, because you see, it wasn't quite in the middle. Anyway, sorry, I didn't mean to get onto that bit, but it just goes to show how difficult it is to simulate chaos in the laboratory. Anyway, but you get the point about when you have a system that is almost, as it were, self-aware, its behavior tends to be much more, you tend to get much more large events than you would expect from the statistics of the small events. And since we're having these lectures in the City of London, of course, a paradigmatic, self-aware, but rather random process is the stock market. And that's exactly why you don't see that kind of Gaussian behavior in the stock market, but you actually see, big swings much more frequently than you would expect if you assumed the stock market was just and various people nodding wisely. I suspect that's what they do. So that's an example of the kind of process. So we need to think about chaos in thinking about understanding the link between weather and climate. This is the original chaotic attractor proposed by Ed Lorenz back in the 1960s to explain the lack of predictability or the challenge of predicting atmospheric weather and why it was that weather forecasts tend to go wrong after only a few days. But I'm not going to I'm not going to use this to talk about predictability and prediction. I'm going to use that's Ed Lorenz. I'm going to use Ed Lorenz's model to talk about the link between weather and climate, to illustrate the link between weather and climate. So here's a view down over the Lorentz butterfly, and the dots are sort of what happened in the system in a particular hour of a Lorentz day. So you can imagine it's a model of the atmosphere, but obviously it's a very idealized, stylized model. And the blue line at the bottom shows you the distribution, so how often you find dots in that value of the x variable of the Lorentz attractor. So you've got this is imagine the particle is moving around in space, and then we're just recording where it is every hour, and then looking down at it. So we're looking, if this is z in the vertical, x in one direction, y in another, we're looking down at the xy plane, and seeing a map of its behavior and building this distribution. And Tim Palmer suggested this, again, I think around the sort of late 90s. Here's Tim Palmer admiring a chaotic pendulum. What happens if you blow on the Lorentz butterfly, so to speak, if you impose an external driver that pushes the Lorentz model just in a particular direction, which is shown by the arrow there. And you can see the behavior, the response to this external driver is to make it more likely that it's going to sit down here in the red area. So the red ones are the ones with the driver. The blue is the original one. So you can see I've just added the red on here. And you can see that with the forcing, it tends to sit around here. So imagine that's wet conditions, that's dry conditions in the atmosphere. The atmosphere tends to sort of hang about in the dry regime a bit more. And you can see that, even though the forcing actually is pushing it in the positive direction, you actually end up with fewer high X events, fewer floods, if you like. But what is interesting is if we actually look at the impact of the forcing, and this is what I meant by the two ways in which we need to think about climate change affecting weather. One way to think about it is to think about the trajectories of the weather, the evolution of the atmosphere that leads to a high-impact event. So imagine a hurricane making landfall in the US. So there's a whole series of events that happen, that hurricane's trajectory, and you can ask, well, what's the role of the external driver, like climate change, in the evolution of that hurricane? And we can think about this in the context of the Lorentz system and say, take away the driver. So this is where we've got that Tim Palmer's blowing on the butterfly, and now we remove it and we look at the same trajectories, and you'll notice they don't go as far in the X direction. Can you see that the green lines peak slightly less far to the right than the red ones? Quite a subtle signal, but I'm afraid we're dealing in subtle signals when we're talking about climate change and weather. The external driver increases the magnitude of these high X events. Yeah? If you just look at one event and assume it's going to happen anyway, the external driver might make it bigger. So that's one way in which climate can affect weather. But at the same time, if I just color in high X events just over a certain threshold, you'll see there's more blue ones than red ones. So the external driver is actually reducing the frequency of these high X events. So these are the two ways in which climate, and they needn't be the same, that's the point. There's two ways in which climate affects the weather. One is by affecting the actual individual behavior of individual events by making them bigger, or making them smaller in some cases. And secondly, by affecting their probability of occurrence. And you need to understand both of these if you're going to understand the link between climate and weather. One of the things I'm actually quite proud of over the past 20 years is sort of in doing this work on understanding the link between climate and weather. Obviously, it's lots of journalists are very interested in this question. Whenever a weather event happens, they want you to answer the question. And back in the early 2000s, I had a lot of conversations with people where they got quite exasperated with me. So can't you just answer the question, is it climate change or not? And I would wander off rabbiting on about, well, it might be making it bigger, it might be, it might be affecting the probability of the event. And what we've seen over the past 20 years is now the journalists themselves are going off and explaining all this. And I think we've really made, testament to the science journalists, surviving science journalists of the UK, that we've actually made a lot of progress in accepting that this is actually just quite complicated, that there isn't a black and white answer, but that doesn't mean, there's no answer. It's an interesting, slightly complicated answer. So there we go, the external driver. In this particular example, won't of course happen generally, it reduces the frequency of high accidents. So this is chaos and the fact that events in our atmosphere are self-reinforcing makes life particularly interesting. It means that you can't just use the statistics of boring events, normal events, to predict what's going to happen at the extreme, and you can also have these two ways in which external drivers affect weather through their impact on the magnitude and impact on probability. So we proposed this sort of way of thinking about the link between climate and weather in 2003, and later that year, in fact, we had a chance to implement these ideas in a much more prominent event, the heat wave that occurred in the summer of 2003, which was actually, it caught Europe very badly by surprise, and you can see it had very serious consequences. Notoriously in France, there were a lot of deaths, but actually this is a figure from southern Germany, where the health system was by no means overwhelmed, but you can see the 2 weeks of the heat wave. You can see the spike in mortality. These are daily death rates. That was a flu epidemic earlier in the year, and you can see during the heat wave, the heat wave was killing people at a faster rate than the flu had been earlier in the year. And as I say, that was actually in southern Germany, which was not the most extreme temperatures. And so we went into this problem and working with Peter Stott at the Met Office and Dahi Stone, who was a postdoc in Oxford at the time, interestingly funded by the Wellcome Trust on an epidemiology grant. So we were using the point of this research as we realized we needed to use techniques from epidemiology, the kind of techniques that we've all got ever so familiar with through COVID, about how do we work out what the role of climate change is in affecting the risk of these weather events. And this shows, apologies for the crudeness of the graph, but that was then, and this is the kind of graphics we got away with in our papers. So the red line is if you just include human influence, simulated summer temperatures, various simulations, so there's 4 of them plotted here. Green is the average if you don't include human influence, so you can see there's a bit of an offset in the climate, but the individual spikes are sort of as big as the offset in the climate, and the black line is what actually happened. And we used this to argue that human influence on climate had increased the risk of this event by around a factor of at least a factor of 2, and best estimate probably more like a factor of 10. But you can see immediately from this figure, there was sort of one event that looked like, yes, the model could do this, but the only way it's not that convincing. And, oh, by the way, I should mention, because Peter would love me to mention it, he's got a great book out. So look for Hot Air by Peter Stott, The Inside Story of the Battle Against Climate Change Denial. Sorry, that's a complete digression. But if you're watching, Peter, you owe me. Okay. The model, the challenge with Stott, Stone, and Allen, I mean, it was a long time ago, but there were plenty of things wrong with that study. And the most obvious was that the model we were using, we were simulating summer temperatures to see how, because when you simulate the world, you can take human influence out and see what happens. So it's sort of, you can do experiments like that. But we were simulating the world with a model that we knew couldn't actually do what happened. It couldn't generate a 2-week heat wave like the one which actually occurred. So we were talking, what I was showing you there was 3-month averages, because that was the kind of thing this model could actually cope with. So that was the one problem. We also had very small numbers of simulations, so we had to make lots of assumptions about the distributions and so on. And again, you're then using statistics from a small number to try and predict what happens in an extreme event, which again, we've just tried to explain with the sand pile. That's not what you want to, that's not ideally what you want to do with a nonlinear system. So the next step was a study actually led by Pardeep Paul, a grad student in the University of Oxford, who suggested in 2004, when our paper came out, He just started his doctorate, and we were also running at the time the climateprediction.net experiment, where we were getting members of the public around the world to run simulations of the climate and send us the data back to Oxford. And that had all got going, and Pardeep suggested that we could apply this network of computers around the world to roll the weather dice lots and lots of times in order to try and address this question of the role of human influence in extreme weather. I think it's important to acknowledge, because for grad students, to remind us not always listen to your supervisor, because I actually advised Pardeep strongly not to do this, because I figured it would be very risky and difficult and slow for a PhD. And so it did take him a long time, to be fair, but he got funding and so on, so he was able to do it. And he did get the last laugh after all. So that was his paper, which came out actually in 2011, which if you do the maths, it was a very long PhD. But it was a great result at the end of it. And I'm going to show you an example, not actually Pardeep's original paper, but one we worked up a bit in more detail, applying Pardeep's approach to the UK winter of 2013-14. This was an extraordinary winter. It broke the record. It was a record-breaking wet winter. You probably remember it. We actually maintain the world's longest daily weather record in Oxford at the Radcliffe Observatory. And here's Ian Ashpole making history, pouring out the flask to record the record-breaking wet rainfall. And at the time, of course, everybody was talking about the link with climate change, and here's David Cameron trying to look scientific or something, and he came out saying he very much suspected this was something to do with climate change, with no particular evidence at the time, but it did sort of motivate the scientific community to address the problem and say, okay, well, was he right? Was there any justification for this? So when we're talking about winter weather, it helps to think about the North Atlantic as a sort of four-sided dice, if you like. And these curves show pressure in different weather regimes in the North Atlantic. So here's one, the sort of northerly cold blast. That's one weather regime. Here's a wet southwesterly, another regime. A very chilly easterly, but gentle but cold winds, and finally nice warm southerly. So these are the sort of four sides of the dice, and the question we wanted to ask ourselves was, obviously what had happened in 2013-14 was we had a lot of this one. The dice kept on coming up on this side again and again and again, and that's what built up the floods. And so what we did was we used a model now, which we were convinced ourselves, a higher resolution model even than the one that Pardeep was using, convinced ourselves the model was able to simulate what happened. So this shows you what actually happened in reality and what happened in one of the wetter members, or the wettest 1% of our large numbers of simulations. So it doesn't happen all the time, but it can do what happened in reality. So having convinced ourselves of that, we then rolled the dice with the model, so experiments in silico, if you like, simulations of, in red, the world as it was in 2013-14, with all the drivers prescribed as the world as they were, in terms of temperature, greenhouse gas concentrations, and the rest of it. And okay, this is back to these return time plots. So this is 1 over the probability of an event of rainfall that high is 1 in 100. Okay, so it's the same plot I showed you with the dice, but it's just now simulations of the weather of that winter, and each dot corresponds to one simulation, which is why it was tremendously helpful to us to have all these members of the public doing these simulations for us, because there's a lot of simulations that need to be done. This is only showing you a small fraction of them. So you can see that the red is simulations of the world as it was in 2014-15, and the blue is simulations of the world as it might have been without human influence. if you sort of reverted to 19th century greenhouse gas concentrations and changed the surface temperatures of the model to an estimate of what the world would have been like back 150 years ago, or back in the way it would have been if we hadn't raised greenhouse gas concentrations. And as you can see, there's a change in the risk. There's a shift from blue to red. It's not huge, around a 40% increase in risk. So this was the bottom line of this study, was that, yeah, human influence had increased the risk of this flooding, the floods that occurred in 2013-14, by a fairly modest amount. So, you know, maybe Cameron got it just right by stroking his chin and looking sort of thoughtful, because it's not a huge signal. There are other stronger ones. And it's not always the result you get. This was the autumn 2000 case, which Pardeep did, and he found a doubling of the risk, 100% increase in risk. But interestingly, the following year, Alison Kay at the Centre for Ecology and Hydrology in Wallingford did a study where she considered how climate change had affected the risk of an event that didn't happen. So she asked, well, we didn't have floods in the spring of 2001. How would climate change have affected the possibility of us having floods in the spring of 2001? And what she found was, interestingly, there was a decrease in risk. And why? Because the heaviest flood events in Britain in the spring occur because of rapid snowmelt. And we don't get that anymore because of climate change. So risks of different events are changing, and they're all changing because of climate change, but they're changing in different directions. And that's really important. Because you could still get a spring flood, but should you prepare for more spring floods is as a result of climate change? And the answer is, well, you've got to go and do some work to find out. And we shouldn't just assume because bad weather happens that it's definitely going to become more frequent. You may remember there was a big argument in 2011, I think, about whether we needed to invest in more snowblowers for Heathrow because of climate change. We didn't, and I think that was the correct answer. Of course, I may be proved wrong by subsequent events, but all the evidence is that actually heavy snow events, such as we had in 2011, I think it was, are actually getting much less likely because of climate change. So probabilities are changing, and it's really important to understand how. And one of the key things that Freddie Otto introduced into this was relating these different ways of quantifying the impact of climate change on an extreme weather event. There's the red lines, which show you the increase in magnitude in the vertical or change in probability in the horizontal. And they both suggest that if we look at the changes, we might reach the conclusion this event has been made much more likely because of climate change, so it's mostly because of climate change. But if we also remember what would have happened in a normal year, we very often find that there's a big contribution from chance as well. And so you can have rather sterile arguments about whether an event is mainly due to human influence and whether it's mainly due to luck or bad luck. And the answer is always, well, it's a bit of both. Understanding how these different things contribute is the essence of what we do in understanding the link between climate change and weather. Which brings us to a very different approach, which I just want to acknowledge, although in the length of this lecture I can't really go into this approach in detail, which was pioneered by Ted Shepherd at the University of Reading. We're all very obsessed by the attribution problem in Thames Valley. But Ted considered if you remember the picture with the Lorentz attractor, the impact of the forcing on an individual trajectory that was already going in a particular direction. What difference did climate change make? And this is what Ted calls the storyline approach to attribution, where you take out or put in the influence of human, you simulate an event and then you take out or put in the role of human influence into that simulation to see what it does to the size of the event. And this is an example which he gave of Hurricane Sandy, Superstorm Sandy, which clobbered New York a few years ago. And this is with observed sea surface temperatures at the time. You can see the intensity of the storm. And this was if you modified the sea surface temperatures to make them more like sort of what they would have been back in the 70s or so. And you can show the storm was intensified by the sea surface temperature. So this is an example of how you can trace out the role of a particular driver. Now, this is not thinking about probabilities at all. This is saying Superstorm Sandy happened, but what we're asking is how did climate change modify what actually happened when Superstorm Sandy went out? I want to get on to what we're doing now, because this is bringing you right up to date to where attribution is going, because all of those studies that I've talked about up until now have been using models that are essentially making a lot of compromises in their representation of the weather, and they tend to be at their weakest when talking about the most extreme weather events. But there are a class of models out there that are in use every day that actually simulate extreme weather extremely well. And those are the models that are actually used for weather forecasting. And if I showed you these two, one of these is a synthetic satellite picture, the other one is a real one, and I asked you, which is which. You have to take a moment to think about it. If you're into this sort of thing, you can tell what the issues are with the model. But that's a weather satellite observation, and this is the European Centre's 18-kilometer ensemble forecasting system. That's the model that up until a couple of months ago, when they increased the resolution to 9 kilometers, the European Centre for Medium-Range Weather Forecasting in Reading was using to generate its weather forecasts twice a day. And the crucial thing about these models is they are scrutinized relentlessly, because if this model fails to simulate an extreme event, well, it's not that somebody gets fired, but there's a SWAT team comes in straight away to say, well, what went wrong? Because they need to get the forecast right. And if you miss events in the forecast, that's the worst. If you miss an event, even if the event's not particularly predictable, if you fail to say that it might happen, then that's a real well in advance. Then that's a real failure of the forecast. So this is the nice graphic produced by Nick Leach, who's here, showing, and whose work I'm now moving on to talking about, showing the contrast between what you get out of a weather forecast model. This is water vapor swirling around over the North Atlantic, and what it would look like in a climate type model here. So if you're thinking about an extreme event like a storm here, you can see immediately it's going to be sort of smeared out, and you're not going to capture the real statistics of the events that actually do damage. So just as an example, I'm going to tell you about the first application of this to a damaging weather event. Nick did start off by looking at a heat wave in February, which didn't like a heat wave in the UK in February. In some parts of the world, the heat wave in February does lots of damage, but it was a UK heat wave, which was interesting meteorologically, but it wasn't particularly interesting to the public. This was an event that was extremely interesting to the public. The heat wave that occurred in the Pacific Northwest in June 2021, work between Nick and Antje Weisheimer, where we saw an excursion out of the distribution of peak summer temperatures that was just several standard deviations out. And you see something like that, that's the time to start thinking about sand piles. Because yes, you could have a random process like that which suddenly does something like that, but you'd have to be pretty unlucky. It's sort of you're trundling along and suddenly you roll a 666. And it caused, the event caused a lot of damage. There was a lot of, the town of Lytton in British Columbia set the all-time Canadian heat weather record and then burned to the ground the following day, I think. It was, and it was also, as far as we could tell, this in the observational record, this was a completely unprecedented event. But interestingly, it was extremely well forecast. This is the forecast of the event, color is temperature. The lines show you pressure. The forecast of the event 3 days ahead basically nailed it. Even the forecast 7 days ahead was showing it was going to be pretty hot. And at 11 days out, again, you're seeing the broad, this was a well-predicted event, even almost a couple of weeks ahead. And even if we look 2 months ahead, this is not forecasting what was going to happen on that particular day, but just looking at what could happen in that season, in a hot day in that season. And you can see it's close to what actually occurred. So we're dealing here with a model that can, unlike many of the other models we were talking about, actually capture the physics of this kind of extreme event. We can convince ourselves even more of that by looking at, say, individual simulations. So that's what happened here on the right. This is one of the simulations in the model, which Nick has carefully picked out because it is the one which is closest to what actually happened. And you can see it matches not only in temperature and pressure, but also this lower plots show you the flow of water vapor in from the atmosphere, from the tropical Pacific, which carried this atmospheric river that carried a huge amount of humidity into the Pacific Northwest, where, because of this anticyclone, it didn't rain, but you had very moist air sitting over, so you had moist air but not raining, which was sort of ideal conditions to build up this really intense heat wave. So the experiment we did, or the experiment that Nick and Antje did, with Chris Roberts, also at the European Centre for Medium-Range Weather Forecasting, you start with the actual forecast. So you're starting with a model you know could do the event, because it did, it forecasted. And then they modified it, subtracting the pattern of warming that we believe has occurred as a result of human influence on climate, and also changing greenhouse gas concentrations to something like 1900 conditions, and then doing the same in the opposite direction, and repeat the forecast to see what difference it makes. And here's the difference it makes. So you can see in both the future climate and the pre-industrial climate, we still see a heat wave, but the loading of the dice is pushing us towards a more intense heat wave in the red, or less intense heat wave in the blue, or conversely, making the odds of a heat wave as large as what actually occurred, higher as a result of the loading. And finally, talking about work done last week, and so this is what our group does a lot in Oxford. Olivia Vashtiayim, who's joining us. I haven't mentioned who's funded different people here, but I will mention who funds Olivia, because that's the Man Group, who are actually based very near to Gresham College. They're funding her work, and she's looking at precursors to what actually happened. So looking within, because you've got all of these simulations, I should have stressed, each one of these is a simulation of what could have happened given the starting conditions, and then all the modified starting conditions at the beginning of the forecast. So each one of these is a simulation with that complicated synthetic Earth that I showed you. And so a huge amount of computing time goes into this sort of thing. And what Olivia's doing is using the fact that we've got all these simulations to ask, what are the precursors to the event that happened, and can we link those precursors to human influence? So if you look carefully here, this is pressure, atmospheric pressure. Red is high pressure, blue is low pressure. And day there, day -8, that means 8 days before the event that happened. And as I approach it, you can see it's about day -6, a coherent pattern appears in the Pacific. Maybe there's a hint of it on day -7, but it gets pretty strong in day -6. And then as I go forward, -5, you can see it moves in there, strengthens, and there's the high pressure 3 days before the event, when it was really predictable there was going to be an intense heat wave, and it builds up, and when you get to the heat wave, actually it's bang on the heat wave. This is asking within that cluster of simulations, what tells us it's going to be a hot one? Yeah, so this is the indicators within the ensemble. So you can see that's clearly one of the triggers. Was a week beforehand, you had this tripole pattern appear, blue, red, blue, and it moved in. That was clearly part of it. And another part was water vapor transport, this carrying water in from the Pacific. This is a much noisier picture here. And you can see, though, around day -6, do you see this orange little feature appearing here, which strengthens, going straight into the Pacific Northwest. And it's really getting strong 4 days before the event. But by the time the event happens, it's all over. So it's not really, it's done its work. It's loaded the atmosphere with moisture, and then the heat wave, and then we had the spectacular temperatures. So, to wrap up, there's a sort of, there's an appeal in this talk as well as just providing you with information, because we can do this kind of thing. We can use state-of-the-art weather forecast models to actually answer the question of what is human influence on climate doing to extreme weather. But it's not done routinely. This was a huge amount of work for a bunch of grad students in Oxford, well, one or two grad students in Oxford to be precise, and of course got done years after the event, because that's how long it takes to get these experiments done. We're all being asked to do something about climate change. And when somebody asks you to do, you should point out to them, again, I keep encouraging you to write to your MP. One of the things you could ask your MP is, why aren't you doing a better job of telling us what climate change is doing to us? Because we could be, it's only a matter of resources, we could be applying exactly the same models that we use for the weather forecast to the question of quantifying changing extreme weather risk. But we need to be doing this every day. We shouldn't just be doing it, when one event happens in one part of the world and somebody happens to get interested. We need to understand understanding extreme weather actually is, I believe, the strongest case we have for developing virtual Earths, for developing computer models of our planet which behave in a way that's actually indistinguishable from our real weather. And we are close to that. We have the tools to do this. It's not an invitation to an open-ended research program. It's a matter of putting pressure on politicians to foot the bill for institutions like the Met Office, like the European Centre for Medium-Range Weather Forecasting, to start doing this on a routine basis, so that we don't end up sort of speculating and arguing over these things. There's just an answer that comes out. When a big, bad event happens, within a few weeks, we should just hear from our forecasting centres, yep, human influence made that event less likely, or maybe made that event more likely, and here's the number. That information could be available to you, but it's not. And that I think you should change. So wrapping up, we can quantify the impact of climate on weather by thinking about loading the weather dice. Attribution of the most extreme events requires realistic models. If you try and rely on crude simulation, averaging up from simpler systems, because of the sandpile effect, you can easily get the wrong answer. And I believe this should be made part of the job of weather forecasting centres to make this happen. Thank you.
Myles, fantastic. That was absolutely fascinating. Scary, but fascinating. I'm sure we've got heaps of questions, so we're going to jump straight in, if that's okay. Now, I've got a question from Paul, who wants to know, we're talking about how climate change is affecting weather. Are there any reasonable studies on weather modification that could aid the negative impacts of climate change?
We're going to be talking about that in the final lecture of this series, so I'm going to punt that one.
Sneaky promo there. Okay. All right, then, let's try this one from Andrew. Which is the greater insurance probability? Megacities flooding or global food systems going to drought?
Well, now you've got to ask that question for other people who work in this in this part of the world who work in the insurance space. But both of them are, it depends on the megacity, depends on the event. Both of them are affected by climate change, and they're the kind of things that we need to know how those probabilities are evolving. And at the moment, because we need to know how to adapt to them and how to deal with changing risks in the future. And at the moment, in my view, our planners are being underserved by the climate research community. I mean, I'm fessing up here that because when we do these climate simulations, we're using models that just can't do these events. So what we should be doing is, and we've got much better models available because we use them for forecasting. So we should be applying the best tools we have available to address this problem. And yes, it would cost more money because it costs computing time and so on. But compared to the cost of preparing flood defenses or preparing for a global food crisis, it's trivial. So we need to understand what's happening, and we need to make the investment to do so.
And that touches on the question I was going to ask you. How prepared are we as a society, as a culture, as an economy, for living with a state of sustained unpredictability? And is the answer to that just to do more science? So
I've not talked about predictability in this lecture, and that would be a whole other lecture about whether climate change is making the weather less predictable. You hear that a lot, but actually the evidence for it is tougher. That's work for the future. We are having to cope with designing things to deal with different climates. So if you're building a building today, it's going to be dealing with a range of weather risks in the early days of its life that will be different from the range of weather risks that building will experience at the end of its life. So that makes things more expensive, it makes it harder for planners to do it, and it makes it really important for people to understand how these risks are changing, which is what this science is all about.
A simple question. Most of my questions are very simple. You're talking about the need for global coordination so we can predict better what the future will be and whether it is due to climate change or natural phenomena. Is there good communication worldwide, or do meteorologists work in isolation?
That's actually a really good question. At the moment we have, climate research is remarkably nationalistic. So we have national climate simulation programs that produce a climate model that they've put together at the end. And that's a good thing in one sense, because it means you have a sort of variety of models and so on, so you get to sort of explore uncertainties in that way. But to do this kind of thing, that's probably not the best way of doing it. You're much better off pooling resources to get the best model you can. And then because of course these models are global. You can't run a model of just one corner of the world. I mean, so you may as well pool resources and do it. You might not run just one, but pooling resources and having just a handful of these forecast models is the way which is the way the forecasting community has gone. I mean, if you like, you can sort of almost tell that weather forecasting really matters because it costs money when they get it wrong. So we've actually had a big winnowing out of forecasting centres over the past 20 years. So we now have really only a handful of countries maintain full global ensemble forecasting capabilities, and other countries just buy in. So I think we need to move in that direction, or rather, one option is that the forecasting community just adopts this and just applies their approach, which is much more global in approach than the way we're approaching climate issues. Because climate research has come out of universities, which is all quite parochial and so on. And whereas this sort of stuff, it's got to be approached in the same way that we approach the weather forecast.
Hi there. I asked the question about the insurance risks that are predictable.
Yeah.
But really my question is, can you use AI to enable evaluation of halting deforestation and increasing forestation?
Yes. So there's an enormous potential role of AI in this because, as Nick is dealing with at the moment, tearing his hair out with the terabytes of data you generate from these simulations. Because imagine we're simulating the whole world at 18-kilometer resolution. We're doing it twice a week, and we're doing 50 member ensembles. It all builds up to ridiculous amounts of data very rapidly. And I think we all recognise that actually analysing this properly will require AI, and that would allow us then, if you've got a realistic in silico model, in a computer-based model of the climate, then of course you can ask the kind of questions you're asking. And you can then play around with it. You can deforest it and see what happens, to weather risk in other parts of the world. But you'll need to do multiple runs in order to do that, because one run is never going to, because of the butterfly effect, it's never going to tell you everything you need to know. So that's where I think the first application of AI to this is just dealing with the big data problem.
It's more a comment than a question, because I live in Miami and we have hurricanes, and they all have, on the news, they always have all the models. And I just want to say that the European model is always the one that's most reliable, rather than all the other ones.
We like to work with the best. I'll pass that on.
We like to end on a positive note there. Ladies and gentlemen, join me for thanking Myles Allen very, very much for such a fascinating lecture.
Thank you.